So now we go to the late morning session. Let's let Sebastian, who came to us all the way from Germany, so let's give him a warm round of applause. Tell us about macros and metaprograms, all the cool stuff.
Thanks. So, my name is Sebastian. I'm a PhD student in Karlsruhe, Germany, and this talk still isn't about Racket. Yet I think I've mentioned Racket quite a few times. So this talk instead is about the lean functional programming language and interactive leanprover. And that last word, I usually assume I have to explain that first, but I mean, here I'm curious with this crowd. So how many of you have heard of interactive leanprovers or proof assistants before? Okay, that's definitely the majority. And of lean specifically, yes, I think. All right. So if you've heard about lean recently, then might have been from one of these articles, like on nature.com, titled "Mathematicians Welcome Computer-Assisted Proof in Grand Unification Theory." If you've not seen this article before, then let me just use that as an example for what people do with these proof assistants. So what's the story here? There's this mathematician, field medalist, actually Peter Scholze, who is working on a new theory that aims to connect different mathematical topics. That's this grand unification, together with a colleague, I should say. And there was one central theorem where they really weren't quite sure about the correctness of their proof. So Peter basically issued a challenge to another crowd of mathematicians who are quite sure about the correctness of their proofs because they verify them using computers, which is the interactive theorem prover crowd. And so a group around Johan Kommelin took up this challenge in Lean and verified it in about 1.5 years' time. And actually, they thought so hard about this proof that they even simplified it a bit. So this is what Lean looks like. It looks a bit like code, right? Like a theorem is a kind of declaration that has a name, it has some very fancy parameters, and after the colon there's a type that describes the proposition we want to prove. And then there's the proof as well, but I mean, this slide is a bit too narrow to contain it. And so Scholze was ecstatic about this result, of course. He said like it was absolutely insane that proof assistants could now handle modern novel mathematics on this level in a reasonable amount of time. Because don't get me wrong, there have been very impressive formalizations of mathematics done in proof assistants in computers before, like the capital conjecture, four-color theorem. But yeah, the support of novel mathematics, this was something quite new. All right, so this is why some people care about proof assistants. And what we will care in the remainder of this talk is fancy notations like this one. And more generally, how we support, how Lean enables mathematicians and computer scientists to express their ideas more naturally using the power of macros. So what does a macro even look like in Lean? And actually there's not just one form, there's like a whole tower of abstractions that build on top of each other, which I think a concept that Racket people appreciate. So the very simplest level, we can say something like, let's introduce a new infix operator, like left associative with some precedence, but let's ignore those details. Let's call the operator plus plus, and it's just syntax sugar for calling the append function. So we can now write something like x plus y, and this is just short for append xy. Okay, so far so easy. It doesn't really look like a macro yet, right? I mean, Haskell can do this too, most other proof assistants, and we don't say that Haskell has macros because of this. It gets a bit more interesting once you realize that this infix.l command is in fact itself a macro for a lower level command, which you call notation. So now we're a bit more explicit at this level. We say there are named placeholders x and y to the left and the right-hand side of our operator, and on the right-hand side of the notation as well, we say where to insert the x and y into the result. And so on this level, we could now also model notation other than just infix operators, like using arbitrary sequences of placeholders and tokens in between them, for example, like on the previous slide. All right. If we go down one more level, we actually get to a command that's called macro. And now we're even more specific of the syntax. We say that the placeholders x and y are terms, as well as the entire notation, the entire macro here. So terms or expressions, that's one of the syntax categories, we call them, that are supported in macros. And so on this level, we could now also write macros in other categories. So for example, the category of commands, which are things that you can write on the top level of a lean file. And yeah, I've already said that infixl itself is a macro, so a command macro that you can write, implement on this level. Yeah, question?
So the term part came from the fact that you said infixl.
Yes.
But the notation part doesn't seem to reflect the termness.
The termness, which level do you mean? The notation keep command?
Yeah, the middle level.
Yes, okay, so notation is still completely specific to terms.
Notation is specific to terms.
Yeah.
Okay, thank you.
And on the right-hand side as well, we are a bit more explicit. So this is something that suspiciously looks like a quotation, right? And in Lean, we also use explicit anti-quotations with the dollar to splice the placeholders x and y, the syntax trees, into this quotation. So and then in fact, on this level, you could now write an arbitrary Lean program on the right-hand side as long as it computes a syntax tree. So we're already at the level of, what's the name again? Sorry. Def macro, basically. Okay, two more important levels. First, we split up the macro command into its syntax and semantics. So we have a dedicated syntax command that just says, introduces new syntax. And at this level, you can really basically write on an arbitrary grammar, whatever you want. And then we, of course, have to give this new syntax meaning, which, for example, we do using the macro rules command. And now, as a single rule, you can see that we also support syntactic pattern matching on quotations, which we use here to destruct our new notation and, again, turn it into the append call. Yeah?
What are the numbers for?
Those are precedences, like parsing precedence, but yeah, let's just ignore them for now. I mean, you can more or less see that maybe it does, it's for left associativity, that this is encoded, but yeah, different topic. All right, the last level I just want to tease, I wanted to say on this level as well, the fun thing about macro rules is that you can in fact add more rules to an existing syntax at any point in Lean, so it has a kind of extensible macros this way. Okay, last level I just want to tease. In this talk, if we replace the macro rules command keyword by elab rules, then we're not strictly writing a macro anymore, a syntax-to-syntax transformation, but actually an elaborator, which is a syntax translation to the core calculus of Lean, which is like the lambda calculus on a lot of steroids. And the main advantage of this level is that we can now actually make our macros type aware, so we can like infer the type of x and y and so on. Yeah, do crazy things. Okay, so that was a lot of levels, but that's really all there is to Lean macros and elaborators. And so all built-in syntax of Lean as well is expressed in one of these stages. And so as the user, you can always go down to the appropriate stage and have all the power and abstraction that Lean itself does. All right. So even though all of this is actually part of a Lean version, Lean 4, that's not been released yet, that's still pre-release, users have already made use of this power. And so let me just showcase a few examples really quick. So the first one might seem familiar from other languages. It's not too small from all over there. All right. So users have embedded an HTML-like syntax into Lean using the syntax command, and then wrote macro rules to translate that syntax to like HTML document generating functions in memory, and used all that to implement a documentation generator for Lean in, I think, a very natural way. So yeah, this is basically like the JSX compiler and other languages, but of course in Lean, the advantage is that you don't need a new compiler. You can just do the left-hand side and immediately start using this new GSL. Yeah?
Sorry, are you going to just leave out the precedence numbers, or is that the actual syntax?
I don't think it's necessary here. This should be the actual syntax. Yeah, like it's only a part. Like the JSX attr is not declared, but this should be the actual syntax.
And the reason that less than, greater than don't have any, the less than in particular doesn't clash is because this is inside the category of JSX element, which is not the same as the term.
So yeah, I think so. Basically, like I mean, in the end, you embed this JSX element into the category of terms. Otherwise, you wouldn't be able to write this. But I mean, no term starts with an angled bracket, so I think it just works out. All right. Another simple example by dwrensha is he used syntax to visually encode a maze in Lean. This one I like particularly. So you have like walls and an exit, and he went further and actually implemented simple tactic macros, which is, so tactics are like the language of proof steps in Lean. And so you now can actually write down a solution for a maze in this very simple style. Just tell it the path to the exit, and Lean will actually double check that this solution is a correct proof. So good luck cheating in this game. All right. So I hope this shows you that you can do some fancy stuff in Lean using macros. And I mean, I don't have to tell you that about macros in general, the Racket users after all. So apart from the relative lack of parentheses, what are some interesting differences in these macro systems? And so I mean, the most noticeable difference in Lean is this existence of a grammar that comes with every macro, that it forces like a static syntactic structure on the macros, right? And we do that to get this arbitrary syntactic freedom, but we actually get some more parts out of this, like we get a structured, concrete syntax tree, even before we expand any macros, which we make use in our tooling, like our language server, and in fact derive more tooling from it. So as a very simple example, if we have an expression like x plus y plus c, using our previous notation, internally this turns into a tree that we print like this. Yeah, looks like x expressions, more or less. So this term plus is just the internal name of the macro of the grammar rule, and as children it has either other syntax trees or tokens like plus and the identifier C, and those are annotated with source code locations. Those are those random numbers, as well as leading and trailing white space. I think you can see how this can be very helpful for implementing tooling. So one way to think of all this is that the grammar really doesn't have to do anything with macro expansion at all, right? Like in Racket, we could say this is just a very fancy reader, and as soon as we're at this S expression level, we could just do regular Racket macro expansion. But what I want to emphasize here is that this is quite different from how other languages work that try to combine macros and non-S expression-based language. So, for example, the Racket-related Repono language, which you might know, as well as Rust, which you also might know, those do not have this separate grammar. They actually discover the structure of the syntax tree to some degree during expansion. So it's a quite different approach. And I think both approaches make sense for their respective use cases. In fact, the Hondo paper is quite explicit about being an example in the middle ground between the syntactic minimalism of Lisp and maximal grammatical freedom. So you could even add just off Lean at the end of the sentence, and then you would have a pretty apt description of this design space. And so even though Lisp, Hondo, and Lean explore quite different these points in the space, I think we still share the goal mentioned in the next sentence, to have a syntax that is both natural and easy to extend. Right, but let me get into a bit more detail about why I think these languages explore these different design spaces, what it enables Lean to do to work exactly like this. So what you need to know about Lean is that actually Lean files are processed command by command, like strictly top-down, like good OC. So in Lean, turns out you cannot reference something like this F before it's being defined, like lexically before that. So this is pretty weird for a modern language, right? Most languages have like more than one pass. But it's actually a property that it shares with most other proof assistants and dependently typed languages. And yeah, there are various technical reasons for why that is. If we accept that, then of course we don't have to worry about syntax, macros being defined after their use either. And so that's helpful, right? Because if we allowed arbitrary syntax for macros, how the heck would the parser be able to parse this if it doesn't know the plus yet? And we are trying to define it in the next line. How would it know that the next line is not part of this unknown syntax? Like, this cannot work with arbitrary syntax, right? And yes, you have to restrict the grammar of your macros somehow if you want to allow this ordering. And for example, the whole paper talks about how to do that. All right, but if we accept that Lean already is a bit particular about ordering, then we can get this arbitrary grammatic freedom. And there are some more consequences I just want to quickly list here. So local macros don't really make sense if we cannot use the syntax we've declared in a command, like if we can only use it in the following commands, right? And similarly, macro-generating macros are restricted in this sense. But yeah, there are some upsides from these restrictions as well, of course. So the implementation gets a bit easier in Lean, especially if you've ever looked at the implementation of a macro hygiene algorithm. You might know that some of these parts are where it gets complicated. So we actually, we took the Racket algorithm and simplified it and optimized it for our needs. All right. So before I conclude, let me talk about one more example where we added a feature to our macro system, not removed something from it. And it's about the irony of Lean being a pretty strongly typed language, but the syntax tree actually being basically untyped. Like, it's an arbitrary S expression exactly to enable all this extensibility. So if we write down a simple macro like this can lead to some issues. So what's happening here? We have a syntax and a macro to go with that. So the macro takes a single identifier and turns that into a new definition of that name evaluating to 0. Okay, that's easy. But it turns out it is subtly wrong. To understand why, we basically have to look into the grammar of the def command and see, oh, after the def keyword, there's actually something more complex than just a single identifier. There's like another optional part, and even if that optional part is not even present, we still have to generate a syntax node to hold both of these parts, and that's like the syntax node for this decal it. And yeah, it turns out if we just write an anti-quotation like here, we get the broadest meaning, which means that it wants to insert a decal it here. And so if we insert an ident anti-quotation value for something where a decal it is expected, then we're creating an invalid syntax tree and things will go wrong. Turns out, this is pretty simple to solve. We can just be more explicit. We can tell the parser, oh, this anti-quotation was meant to be a placeholder for an identifier, and then it will parse it as such and create the syntax node around it. But it's still pretty terrifying, right? Like, we shouldn't need to think about this on this level. And it's also ironic because, I mean, Lean has the grammar of the left, the right, and set, right? It should know that this anti-quotation is for an ident, and this previous anti-quotation was for a decal it. So, transferring the static knowledge between two places, don't we have type systems for that? So that's what I recently did. I implemented a new type, T syntax for type syntax, which knows what kind of syntax it is transporting. And so we introduced that. It's a simple wrapper around the untyped syntax tree. That part still exists. But we introduced now use T syntax wherever we can. And so this original macro now becomes an actual type error, where we say, well, it is actually an idle syntax, but I expected a decollate syntax at this point, and so your macro will be rejected. Okay, but it turns out you can use the type system not only to reject invalid macros, but to repair them as well, because Lean has this system called implicit coercions, which tell it how to turn one type into another. So we can actually install a coercion which says, well, how can we go from an idle T syntax to a decollate T syntax? Well, we do that via this function, which uses a quotation. And as soon as we do that, we can now actually write down the original macro again, which used to be wrong, but now we will automatically fix this type error by importing this function call, and thus fix the syntax tree as well. Okay, I think that's all I wanted to talk about. So I hope I showed you that Lean's macro system is quite similar to Racket's, and in fact derived from it, as well as Rust, I should say. And yet there are some fundamental differences, right? And so in general, I would say Lean is a bit more focused on this interpretation of syntax, and we're a bit less focused on some advanced macro features that are listed that Racket has, but Lean does not. And recently we also made macro programming safer by introducing this typed syntax system. Okay, thank you. Questions?
You gave an example of macro. So you kind of take for granted that we love macros, so of course we're going to live Lean macros, and of course that's true. Putting that aside, you gave kind of an example of a cute, weird macro in the maze thing, and then the documentation one that has the JSX. Would you say that it's common for Lean programmers to actually define macros? There's this kind of folk wisdom among Lisps that macros, they're for people that implement libraries, not normal people. It's something that we try to do at Racket is to help people understand that no, you need a macro too. Define the syntax rule is great. You should define your own little things. You should define your own little systems. Is it typical for Lean programmers to actually use these? Like that guy you mentioned who did the proof in only 2 years. Did he define any macros?
That's a great question. So turns out that proof was actually done in Lean 3, which did not have those macros yet.
So it would have only taken 6 months.
Yeah.
And then at 18 months to debug the macro.
Yeah, exactly. Right. So what mathematicians usually use is this notation level, which did exist in Lean 3, and as I said, it exists in most other proof assistants. So those they definitely make use of. But we've already talked about quite a few notations that mathematicians want to write down that they can't in Lean 3, for example, but would be able to write down using the more general macros of Lean 4. So yeah, I think for mathematicians, they constantly introduce new notation and really complicated notation with complex binding semantics. So they should be very happy about this. Then there's computer scientists, of course. I would agree that they should probably be a bit more careful about introducing macros. I guess it would mostly be about really embedded designs with domain-specific languages like HTML, or if you want to prove something about a language, then of course it's great if you can just embed it into a Lean file. I would say those are the main use cases of macros for computer scientists using Lean.
Just want to say that Lean 3 does have limited metaprogramming capability, and I do use it for doing technical stuff. Yeah, so.
Yeah, the maze thing is sort of a toy example
Sure.
of ASCII art macros, but there are some cases where I can imagine wanting to be able to actually write something with sort of not you can't obviously write it visually as a picture, but sort of have a visual example of the proof. Maybe that's not necessarily good for real proof, but to sort of picture it, I guess.
Yeah, that's a great. So there are definitely some parts like, I don't know, category theory, string diagrams, where you really want to work visually. I guess even with macros, it will get hard to just put that into text.
Yeah, that's what I was thinking.
Yeah, so one other aspect that Lean is exploring parallel to macros to input is to just give you a nice output of proof steps, of intermediate goals which we render in HTML. And so there you could display a string diagram using a very natural way, but that would not help you for inputting the original proposition.
So tactic-based proving is a form of metaprogramming as well. Like you're building up a term. Certainly in definitely fixed system like Lean, you're building up a proof term. So is there a connection between the metaprogramming in macros and the metaprogramming that's going on under the hood when you execute a tactic-based proof?
Yeah, that's definitely correct. Let me just go back to this example. Fundamentally, the primitive tactics are all elaborators. They have to work with the core calculus, right? So most tactics are not macros in the sense of the syntax, but yeah, all the I would say the surface level tactics are in fact macros, like this one, and so our tactic interpreter executes tactics step by step in Lean4 is actually just macro expansion. So the macro expander drives the whole tactic execution. Yeah.
So, the sort of flip side of Jay's question is, mathematicians have a terrifying desire to invent notation, and now you've given them that power. and so, it's kind of right. And so there's a point I'm trying to get to, which is, when you open a book, a math book, right, you often end up spending the first little while. There's a reason why they always define their notations and so on up front. Because they're saying this is the language of the rest of the book, right? And, we've all read math books where they take something and put like juxtaposition means something and something else means something else and so on. So that sounds to me much more like a hash lang mechanism. And I wonder if you're going to have this kind of unfettered ability to write things, does it not perhaps make sense for you to be thinking about adding something more like hash lang? So you declare like this is the language in which the rest of this file is. And then instead of just some random selection, especially the library stuff. Just wondering what, you're clearly learning from the Racket system and moving ideas over. Is that an idea that's on your list as well?
Yeah, we've definitely been thinking about adding hash lang, something like that. I'm not sure if mathematicians would think in this way. I think like they often integrate really different parts from mathematics in a proof, right? And then they probably want to use all those different parts that maybe have not been combined before and just use it in a document. So I'm not sure, like this might be a bit too static, just thinking in hash lang.
So if I import from two different files, and each of those files contains macros, do I inherit both of those macros as well, or are the macros scope the files?
Right, so you can scope macros in Lean4 and syntax, so that you have to explicitly open them, but you can also just put them on the top level, and then yes, you will get all the macros from both imports.
Okay, it looks like we've got perfect timing. Let's thank Sebastian.